4 questions. In the 2024 UGC NET Economics exam alone, 4 direct numericals were pulled straight from the mathematics of risk and uncertainty. To master these calculations, we first have to reconcile a central contradiction in economic behavior. Consider a farmer in Bihar paying a 5,000 rupee premium for crop insurance, alongside a Mumbai day trader buying highly volatile speculative options. The farmer intentionally guarantees a lower net income to avoid loss. The trader deliberately risks capital for a fractional probability of a massive payout. Standard microeconomic theory dictates that both individuals are acting with perfect rationality. To understand why, we have to discard simple expected monetary payouts and analyze how human beings actually process variance through expected utility. Calculations for the most heavily weighted numericals in Unit 1 rely entirely on this divergent mathematics. In 1921, economist Frank Knight established a strict boundary between two concepts that are often confused. He defined risk as a scenario where outcomes have known, measurable probabilities. We have historical data for monsoon failures, or the strict mathematical odds of rolling dice. Uncertainty applies to events where probabilities simply cannot be assigned, like a novel virus or an unpredictable geopolitical shock. Standard actuarial insurance models break down completely under true uncertainty. Under measurable risk, the basic analytical tool is expected monetary value. We calculate this by multiplying the probability of an event by its raw financial payout. However, the St. Petersburg paradox demonstrates that human beings consistently refuse to pay large sums to play a game with an infinite expected value. This happens because the human mind doesn't value every additional rupee equally. Bernoulli observed that 100 rupees is life-changing to a pauper, but irrelevant to a billionaire. This insight, that the subjective value of wealth diminishes as you accumulate it, led to the development of expected utility theory. Instead of averaging the raw money, we multiply the probability by the subjective satisfaction, the utility that the money provides. This coordinate plane maps wealth on the x-axis against the utility derived from that wealth on the y-axis. For a risk-averse individual, like our farmer buying crop insurance, the utility curve is drawn concave, bending distinctly downward. This geometry shows falling marginal utility. Initial income provides immense satisfaction, but subsequent gains yield diminishing returns. A risk-neutral actor evaluates purely unexpected monetary value, represented by a linear blue line. For the risk-loving speculator, the curve is convex, bending aggressively upward. This convex shape indicates a rising marginal utility of income, where the prospect of moving from average wealth to extreme wealth carries disproportionate psychological weight. But economic reality is rarely this tidy. The same individual who pays for health insurance might also spend thousands on a high-stakes lottery ticket. This contradiction suggests our utility curves aren't fixed. They shift based on evaluating potential gains or painful losses relative to current wealth. This behavioral nuance is the foundation of prospect theory. For your exam calculations, identifying whether a given utility function is mathematically concave, linear, or convex is the mandatory first step before applying any formulas. Let's isolate the risk-averse concave curve to calculate the two most tested metrics on the NET exam, certainty equivalent and risk premium. Plotting expected value on the x-axis, the midpoint of the chord between two outcomes gives our expected utility. Extending a line directly to the curve finds the utility of expected value. This vertical gap, expected utility being strictly lower, is Jensen's inequality. Because of this gap, a guaranteed smaller sum of money provides the exact same utility as the risky gamble. This is the certainty equivalent. By tracing horizontally from expected utility back to the curve and dropping down to the x-axis, we locate it mathematically. The difference between the expected payout and certainty equivalent is the risk premium. This highlighted distance on the x-axis represents the financial penalty a person absorbs to eliminate variance. Risk premium equals expected value minus certainty equivalent. Because a risk-averse curve bends downward, the certainty equivalent always falls left of the expected value. Consequently, the risk premium is always a positive number. Classifying a curve as concave confirms risk aversion, but economists use Pratt measures to quantify the exact intensity of that aversion at different wealth levels. Absolute risk aversion is derived directly from a given utility function. Calculate it by dividing the negative second derivative of utility by the first derivative. The most common error in exam calculations lies here, with this leading minus sign and the double prime in the numerator. Because a risk-averse function is concave, its second derivative is mathematically negative. That minus sign is required to cancel it out, ensuring the final measure of absolute risk aversion is a positive value. Relative risk aversion evaluates risk tolerance against a percentage of the individual's total wealth. The formula simply multiplies the existing absolute risk aversion value by x, representing the wealth variable. When dealing with a natural log utility function, a frequent exam scenario, absolute risk aversion decreases as wealth rises, known as DERA, while relative risk aversion remains strictly constant. Memorizing these derivative structures is the only way to quickly classify utility functions and solve the advanced numerical variations in Unit 1. Let's review the conceptual traps examiners routinely deploy to test your grasp of these mechanics. Asserting expected utility equals the utility of expected value is stamped incorrect for risk-averse individuals. Jensen's inequality dictates that expected utility is strictly less than the utility of expected value for any concave function. Equality requires a risk-neutral, linear utility curve. The second common trap is the claim that a risk-averse person has a certainty equivalent greater than the expected value. Because they penalize variance, their certainty equivalent is inherently less than the expected value, creating the positive risk premium they are willing to pay for safety. Here is the compiled list of the core formulas required for Unit 1. Take a screenshot for your revision notes. By mapping the geometry of these utility curves and isolating the derivatives, you eliminate the uncertainty from these questions, locking in your marks for the UGC NET exam.